Welcome in, everyone. Whether you are prepping for a massive engineering meeting or trying to catch up on the latest manufacturing tech, or, maybe you're just insanely curious about how the physical infrastructure of our modern world is actually built, you are exactly in the right place.
Yeah, we have a great deep dive for you today, focusing on a space that most people never see. But it really impacts almost everything around us.
Exactly. We are looking at the realities of industrial machining today. And I think when most of us think of cutting tough industrial metals, the instinct is usually just to assume we need a harder tool, right? Like if you have a tough piece of steel, you go find an even harder piece of metal, force them together at high speeds, and just let raw strength win the battle.
Which is the conventional logic.
Yeah.
But today's deep dive completely shatters that. We are basing our discussion on a highly technical guide we've been reviewing. It's titled, Optimizing ISCAR Insert Geometry for Difficult Materials.
And what this source proves is that raw toughness is, it's no longer enough to survive in modern manufacturing. It is actually all about geometry.
Right. Toughness is just the baseline requirement to even enter the arena at this point. I mean, we are looking at a level of manufacturing where we are cutting aerospace-grade alloys and hardened steels.
Materials engineered specifically to resist being cut or deformed.
Exactly.
Okay, let's unpack this. Our mission today is to explore the hidden, almost microscopic world of cutting tool angles and edges. We are going to look at how ISCAR, which is a global leader in metalworking, engineers highly specific shapes to conquer the absolute toughest materials on Earth.
What's fascinating here is that when you zoom in on that cutting zone, the exact point where the tool meets the spinning metal, we aren't just cutting metal in the traditional sense.
We are managing heat. We are managing friction.
Yeah, and we are dealing with physics at absolute extreme levels. I mean, temperatures can easily reach 1,000 degrees Celsius.
That is insane.
It really is. And the geometry of the cutting insert, the actual physical shape of the tiny piece of carbide doing the work, that dictates whether an operation is a success or a catastrophic failure.
Taking a quick step back, it probably helps to understand what carbide actually is, since the source references it constantly. Tungsten carbide is the industry standard material for these inserts. It's essentially a matrix of extremely hard powdered metals baked under immense pressure.
Right. It is incredibly wear resistant, but it can also be brittle if the physical shape of it isn't supported correctly.
And to understand why that shape matters, we really need to define the enemy here. So what actually makes a material difficult to cut on a molecular level?
The primary trait these difficult materials share is high strength at elevated temperatures. With standard metals, the friction of cutting generates heat, the metal softens, and it just becomes easier to shear away.
But difficult materials don't do that.
No, they don't. Materials like those used in jet turbine engines are designed specifically to operate in extreme heat. They hold onto their structural integrity even when they are literally glowing red hot on the lathe.
Wow. And the text notes that these materials also suffer from extremely poor thermal conductivity, right? The heat doesn't bleed off into the rest of the workpiece.
Exactly. In a standard steel cutting operation, the metal chip that peels away carries about 80% of the heat with it.
So it acts as an evacuation system.
Yeah, precisely. But with poor thermal conductivity, the heat stays trapped right at the cutting edge of the carbide tool, and it just continuously bakes it.
The source also highlights strong work-hardening tendencies. And to visualize this, it's a bit like, imagine kneading dough that suddenly turns to concrete. The harder you work it, the denser it gets.
That is a great analogy. The sheer mechanical act of the tool pushing into the metal causes the molecular structure of that metal to compress and harden instantly ahead of the cut.
And then you add natural abrasiveness to the list.
Right, which acts like microscopic sandpaper, just constantly wearing down the physical edge of the tool.
And finally, you have the tendency for these materials to form long, stringy chips when they are cut, rather than breaking off neatly into small pieces. When I read about those long, stringy chips, the image that came to mind wasn't wood shavings. It's more like trying to cut melted taffy that just wraps around your knife.
Yes, or a continuous ribbon of razor-sharp steel wire. It instantly coils back around the spinning machine chuck, the workpiece, and the tool itself.
Which sounds like a massive safety hazard.
Oh, it is. And it's a really quick way to destroy a piece of equipment worth hundreds of thousands of dollars.
So the culmination of all these traits, the heat, the work hardening, the abrasive wear, and the razor wire chips, that is why you cannot use a generic blunt cutting tool.
Right. Geometry becomes the critical control lever. The microscopic angles molded into the carbide, Inserts control the cutting forces, manage the heat generation, force the chips to break, and ultimately determine how long the tool survives.
Here's where it gets really interesting. Because inside the design of these tiny tools, there is a massive tug of war happening. It's an ultimate balancing act between having a sharp cutting action and having edge robustness.
Yeah, you want the edge sharp so it cuts cleanly and effortlessly. But the sharper you make a piece of carbide, the more fragile and prone to shattering it becomes.
And the source breaks down how ISCAR navigates this spectrum of sharpness versus strength. So on one end of the spectrum, we have what are called positive rake geometries.
Right. And a rake angle is essentially the angle of the tool's top face relative to the metal it's cutting. A positive rake means the tool face slopes away from the cutting edge, creating a thinner, sharper, more wedge-like point.
Looking at the guide, these positive rakes are absolutely critical for minimizing heat buildup and limiting that work hardening effect.
Exactly. Because they are sharp, they slice cleanly rather than plowing into the metal.
Yeah.
That keeps the power consumption of the machine low and promotes very smooth chip flow.
So they are heavily utilized in finishing and semi-finishing operations. When the goal is to leave a mirror-like surface quality on a final part, you need that scalpel-like precision.
But the trade-off is that because that edge is thin, it lacks the structural mass to absorb heavy impacts or deep, aggressive cuts.
So for those tougher, more brutal roughing applications where you were just trying to remove as much metal as quickly as possible, the guide shows ISCAR shifting to moderately positive or even neutral rake angles.
Right. This flattens the angle out. It puts a much thicker block of carbide directly behind the cutting edge to absorb those massive forces.
And to further protect that reinforced edge, they employ edge honing or chamfering.
Yeah, which involves microscopically rounding off or beveling the absolute tip of the cutting edge. It removes the fragile microscopic point, giving the edge the structural integrity to survive impact and resist notch wear.
Notch wear, which is that specific type of failure where the abrasive outer scale of the metal grinds a localized groove right into the tool.
Exactly.
But the immediate question that raises is about efficiency. If you make the edge blunter to survive the impact, it stands to reason that you generate more friction, more heat, and potentially more work hardening.
You would think so. But the source details how ISCAR balances this bluntness by engineering very specific chip breakers right into the top surface of the insert.
I love the descriptions of these. Chip breakers are these complex, microscopic landscapes of craters, ridges, and valleys molded directly into the carbide.
They are. The reinforced edge takes the initial brutal impact of the cut, but as the metal chip flows over the tool, it hits these molded ridges.
The geometry physically forces the continuous ribbon of metal to curl back on itself tightly until the tension causes it to snap into a small, manageable piece.
So it allows you to maintain the cutting efficiency of a sharp tool while keeping the structural strength of a blunt one.
Having established this physics tug of war, I want to dive into the custom solutions detailed in the ISCAR arsenal. The source breaks down how they tackle specific extreme materials, and I really want to explore these matches because it moves us from theory into real-world application.
Let's do it.
Let's start with the heavy hitters of the aerospace and medical industries. Titanium and heat-resistant superalloys, commonly known as HRSA.
These materials are the backbone of jet turbine engines and orthopedic implants precisely because they do not degrade under extreme heat or stress.
But that makes them a nightmare on the shop floor.
An absolute nightmare. The extreme heat generation at the cutting zone combined with poor thermal conductivity means the carbide tool takes almost all the thermal punishment. They're also incredibly notch sensitive.
Meaning if the tool wears unevenly, it will fail catastrophically in seconds.
Right, so based on the tug of war we just discussed, the solution for titanium and HRSA has to lean heavily toward sharpness to minimize that friction.
The guide specifies highly positive rake geometries to slice through the material rather than pushing it.
And it also emphasizes the need for a very narrow contact area at the cutting edge. By keeping the area where the chip rubs against the tool as small as possible, you minimize heat transfer.
Which allows machinists to utilize a concept called chip thinning. This is a fascinating mechanical trick. Essentially, by manipulating the angle at which the tool engages the metal, say, at a 45-degree angle, instead of straight on the physical load of the cut, is spread over a longer section of the cutting edge.
Right. The metal chip itself becomes thinner but wider.
You remove the exact same amount of material, but you distribute the intense heat over twice the area of the carbide, preventing it from melting a single microscopic spot.
To achieve this, ISCAR utilizes specific geometric designs. The guide highlights the Logic 6 turn series, specifically the M3M and F3M geometries.
Those are molded to provide heavily optimized chip control for these aerospace alloys, right?
Exactly. And the Logic 6 turn system is particularly interesting from an economic standpoint. Instead of a standard insert with 2 or 3 usable edges, this geometry provides 6 distinct cutting edges on a single insert.
So when one edge wears out, the machinist just rotates it to a fresh one.
Yes. By increasing the number of edges, it fundamentally changes the tooling economics of a factory floor without sacrificing that critical positive rake angle.
The text also points out the Hilly turn system for these materials, which is engineered to lower radial forces.
Radial force is the energy trying to push the tool straight back away from the spinning workpiece. If that force is too high, the part deflects, bends, and chatters.
Chatter is a massive problem with titanium, as the metal naturally wants to vibrate during a cut, and to combat this, the guide details ISCAR's whisper line turning tools.
Those are really cool. They aren't just shapes. They are physically engineered tool holders containing dampening mechanisms.
So they suppress the vibration frequencies before they can ruin the part.
Exactly. Now, moving beyond the aerospace realm, the source shifts focus to a material ubiquitous in almost every industry, from food processing to marine engineering.
Stainless steel. It presents a completely different set of behavioral challenges compared to titanium.
It does. Stainless steel is notorious for rapid work hardening, but its most dangerous characteristic is the production of those long, stringy, razor-wire chips we discussed earlier.
Right. If you try to use the razor-sharp tools designed for titanium on stainless steel, the chips will often just slide right over the smooth, positive rake and immediately wrap around the machine chuck.
So the geometry must shift to manage this specific behavior. ISCAR deploys medium positive rakes for stainless applications.
The tool still needs to be sharp enough to cleanly shear the metal and avoid excessive work hardening.
But the overriding priority is aggressive, highly effective chip breakers. The geometry has to actively force that stringy, ductile stainless chip to hit a physical wall, curl tightly, and snap before it can become a hazard.
And it has to do this even during interrupted cuts. For example, if you are cutting across a metal cylinder that has a hole drilled through it, the tool is repeatedly smashing into a solid edge and then cutting air, over and over.
That is brutal on a tool. The Logic Turn MF and MM geometries are highlighted in the guide as the standard for finishing and media machining in stainless steel. They are specifically designed to handle those interrupted impacts without the edge shattering.
Hilly turn system makes another appearance here too, but for a different geometric reason. It features a helical cutting edge. Instead of the straight line, the edge twists, much like a spiral staircase.
And that twisting shape naturally reduces the initial cutting pressure. As it engages the metal gradually, rather than all at once, it cleanly shears the stainless steel.
Which drastically improves the final surface finish of the part.
Absolutely. Let's pivot to the final category of extreme materials the source covers: hardened steels and abrasive cast irons. The physics of cutting these materials represent an entirely different battleground.
Yeah, we are no longer fighting heat and stringy chips in the same manner. We are fighting extreme, unyielding hardness.
The sheer physical force required to penetrate a piece of hardened steel means that if you use a sharp, thin, positive rake edge, the carbide will instantaneously snap off.
Edge collapse is the primary enemy. The solution here abandons sharpness in favor of absolute brute strength.
The guide details the use of robust, heavily reinforced cutting edges with highly controlled, often neutral or slightly negative rake angles.
A negative rake, meaning the tool face actually slopes toward the metal.
Exactly. You are utilizing the maximum structural mass of the carbide block to simply blast through the hardened metal, relying on the raw power of the machine tool.
ISCAR deploys their Logic Turn RM geometries for this brutal work. But looking at the source, there is a massive operational shift happening in the industry because of these specific, robust geometries.
Historically, once a piece of steel was heat-treated and hardened, it was considered too tough to cut on a traditional lathe. The traditional workflow required machinists to take the hardened part off the lathe and move it to a cylindrical grinding machine.
And grinding utilizes spinning abrasive wheels to slowly rub away micrometers of material at a time. It is a notoriously slow, messy, and incredibly expensive bottleneck in the manufacturing process.
Right. It requires separate machines, separate coolant systems, and specialized operators.
But by engineering these highly robust RM geometries alongside advanced wear-resistant carbide grades, this hard-turning operation has become so reliable that factories are entirely skipping the grinding phase.
They are aggressively cutting hardened steel directly on the lathe and achieving the final precise dimensions in minutes rather than hours.
Taking an entire expensive machine out of the supply chain just by changing the microscopic angle of the blade is a staggering improvement in productivity.
It really is a game changer.
Yeah.
And having covered the diverse material challenges, the source guide pivots to the operations themselves. It emphasizes that the physical environment of the cut is just as critical as the material being cut.
It specifically examines grooving and parting operations. This is where a tool is plunged straight into the side of a metal cylinder to cut a deep groove or to slice a finished piece entirely off the main bar.
Grooving and parting put uniquely intense stress on the cutting edge. In a standard turning operation, you are skimming along the side of the metal, meaning the chip can easily fly away into the machine enclosure.
But in a grooving operation, you have full width engagement. The entire front width of the insert is buried deep inside the metal. The heat is entirely trapped, and the chips are trapped inside the narrow trench they are creating.
If a chip gets trapped in that trench, it will instantly bind, shatter the carbide tool, and likely ruin the part. The guide details ISCAR's cut grip system to solve this.
Specifically calling out the F, M, and R geometries.
Right. Because the tool must reach deep into the metal, it utilizes a narrow, highly rigid blade design that won't flex under the massive pressure.
The true engineering marvel is on the top surface of those narrow inserts. The geometry is aggressively molded to physically fold the metal chip inward into a V or W shape as it forms.
By folding the chip along its center, the chip actually becomes narrower than the groove it just cut.
This allows it to slip out of the trench and evacuate efficiently, which is absolutely vital when parting off sticky materials like stainless steel or HRSA.
So what does this all mean? If we connect this to the bigger picture, it becomes clear that tool geometry does not exist in a vacuum. It is one variable in a complex manufacturing ecosystem.
The source emphasizes that even the most advanced geometry will fail if you do not account for the stability of the machine tool itself.
Precisely. If a factory is running lighter, older, or less rigid machine tools, they are forced into using more positive, sharper geometries just to keep the physical cutting forces low enough to prevent the machine itself from flexing and vibrating.
Conversely, if they are taking heavy, deep cuts on a massive, highly rigid industrial lathe, they can and should demand the stronger, more robust neutral edges.
The parameters of the cut are equally vital. The depth of the cut and the feed rate, how aggressively the tool is being pushed into the spinning metal, must match the design intent of the chip breaker.
Because if you don't push the tool hard enough, the metal won't hit the ridges of the chip breaker with enough force to snap, resulting in the razor wire problem.
Yes, and the source also highlights one massive operational multiplier: high-pressure coolant.
We aren't just talking about splashing liquid on the metal to keep it from getting warm. We are talking about firing a laser-precise jet of coolant at over 1,000 psi directly into the microscopic gap between the cutting edge and the metal chip.
At those pressures, the coolant acts as a physical kinetic wedge. It gets under the chip, lifts it away from the tool to drastically reduce heat transfer, and actively assists the geometry in shattering the metal and blasting it out of the cutting zone.
The end result of getting the machine stability, the parameters, the coolant, and the geometry all aligned is perfect predictability.
Exactly. ISCAR engineers these geometries to operate within highly defined cutting windows. When a shop matches the right geometry to the right material and runs it precisely within those parameters, they achieve repeatable, flawless results.
In the world of industrial manufacturing, predictability directly translates to profitability.
It does. Synthesizing everything we've covered today, it becomes abundantly clear that machining the most difficult, heat-resistant, and abrasive materials on the planet is not an exercise in brute force.
Slapping the hardest metal you can find against a spinning workpiece is a recipe for failure. It is instead an elegant, highly engineered dance of rake angles, microscopic edge preparations, and top-face chip breakers.
ISCAR has built their specialized lineups. Whether it is the multi-edged Logic 6 turn, the vibration-suppressing whisper line, the helical shearing of the Healy turn, or the chip-folding cut grip system to prove an undeniable point.
In the incredibly harsh, high-stakes environment of the modern shop floor, raw toughness is a prerequisite, but microscopic geometry is the true king.
This raises an important question for anyone listening who works in engineering, process optimization, or simply wants to understand how our physical world is shaped. Understanding the underlying physics, why thermal conductivity matters, why a chip wraps, why work hardening destroys a tool, is what separates a functional operation from a highly productive one.
When you deeply understand the physics of the problem, you can purposefully select the geometry that masters those physics. It is genuinely incredible to think about the level of technological complexity molded into a piece of carbide the size of your fingernail. We have spent this entire deep dive examining how carefully engineered these static geometries must be to survive extreme environments. But as material science and artificial intelligence continue to advance rapidly, it leaves you with a fascinating thought.
Where are you going with this?
Will we eventually see smart cutting tools? Imagine tools utilizing advanced piezoelectric materials that can dynamically shift their own microgeometry mid-cut, physically adapting their rake angles and edge hone in real time in response to the fluctuating heat and pressure of the metal they are shaping. It is something to think about the next time you hold a perfectly machined piece of technology in your hand.
That is a truly compelling concept to leave on, and a reminder that manufacturing is constantly evolving.
Thank you all for joining us on this deep dive into the microscopic world of cutting tool geometry. Keep questioning how the infrastructure of the world around you is built, keep digging deep, and we will catch you on the next one.